My name is Hovsapian. I'm from Idaho National Lab. I'm going to give you a couple of examples of the different kind of microgrids we look at, show you the design evolution that we went through from, I'm going to give one example of a microgrid where we used hardware in the loop and controller in the loop approach to test for resiliency. Then I'm going to show an example of a microgrid where we start using resiliency metrics in order to help us design. And then I'm going to third example, which is one of the new microgrid that we're designing, that's going to show how we use a multidimensional resiliency metrics in order to allow us to increase the resiliency of the system. Just a quick overview of the capabilities at the Idaho National Lab. We have a number of the real-time simulation tools that we have from OpenRT, RTDS, Typhoon that allows us to interact and integrate those tools together in order to help us better design microgrids. We're taking advantage of each tool's resources and capabilities, from looking at a communication all the way to hardware in the loop and controller in the loop type testing. The approach we do is we have an integrated approach to those tools where we tie those tools together, and in order for us to look at it from not only the tool itself, but how do we use the communication layer. More and more we're getting with integrated system, more and more it becomes important for us to start looking at the communication protocols that we use, not only from the resiliency perspective, but also from a cybersecurity perspective, is how to protect those communication in order to make sure that the system operates by design. And then tying it to the other kind of hardware in the loop and controller in the loop testing, utilizing those tools. One of the projects I was going to talk about is the Red Cross evacuation route in Northern California. This was a joint project with Siemens, PG&E, and Tesla for storage. In this project, what we did is we utilized hardware in the loop and controller in the loop approach in order to test the resiliency of the microgrid. So what we did is we designed the microgrid as a digital blueprint in a real-time simulation environment, and we went ahead and brought all the hardware that are associated with this microgrid, and we tested it under different kind of grid scenarios, all the way from a grid connect to black start, resynchronization with the grid, what-if scenarios, in order to test the resiliency before we deployed it. So a lot of the controller that was utilized in those protection devices was developed, tested in this digital blueprint environment with actual hardware prior to the deploying it. So that's a risk mitigation approach of how do we design and test microgrid before you deploy it. And this is the digital blueprint of the microgrid that was designed, and then we start testing other different kind of test scenarios in order to make sure that it's resilient and it can address those conditions prior to deploying it. Another benefit we got with this one as well is prior to deploying it, is we also got the operator of this microgrid that came in and they ran it. So in actual utility system, you won't be able to have that luxury of putting the operator and doing what-if scenarios and bringing the system down. Utilities won't like that. Where in this case, being in a digital blueprint environment, you're actually using the hardware and the controller in a controlled environment to train the operator prior to deploying it. The next microgrid I want to talk about is where we took similar approach to what we did with the Red Cross evacuation route microgrid, except in this case we went ahead and used resiliency metrics in order to help us decide how do we want to reconfigure or design the microgrid. In this case, what we have is a distribution system that it has two interconnects from the transmission side. In the event of a fault condition, it will disconnect from the transmission line and will become an islanded microgrid in essence, and it will do smart reconfiguration in order to maximize the critical load that needs to be running. So it will take into account all the critical loads that's critical for it to utilizing its local generation. In this case, we have a hydro for local generation. And what we did is, this is the first time we start taking now the communication. So we did the actual hardware that's going to be used for protection, but on top of it, we use the communication protocols and the communication devices and how we're going to do the smart configuration. So in this case, we had, before it goes dark, when we disconnect from the transmission side, we wanted to do a smart reconfiguration islanding in order to keep the critical load up and running. And those are some of the critical loads and the approach that we took in order to how do we do smart islanding and reconfiguration to keep those critical loads up and running once it gets disconnected. And once the transmission side is back up and running again, without going dark, how do you synchronize back to the grid and reconnect? This is some of the testing and the hardware that we tested. This shows the 4 run-of-the-river plants that they have, and some of the PMUs from the transmission side and the micro PMUs on the distribution side that we utilize in order to first design the microgrid and analyze it prior to deployment. This is the black start testing that we did. That's one of the things that the utilities wanted to make sure, can we do the black start using the run-of-the-river plant. This is the test that we used using the hardware for that environment. The next thing I want to talk about is the new microgrid that we started developing. This is part of the grid modernization activity for Department of Energy, where we're looking at how do we design resilience microgrid. In this case, it's a joint project between us and Idaho National Laboratory, where we look at it, two integrated microgrid, network microgrid that ties together and in a zonal system. So in the event of a fault, how do you island certain zone of the microgrid in order to increase its resiliency? In this case, we're taking similar approach as we did before. Now I'm going through the evolution. We'll learn a little bit more from the previous project. In this case, what we're doing is we're looking at the multi-dimension of the microgrid. We're taking into account not only in the resiliency, we're looking at the multi-dimension of the historical data, the data of the neighboring microgrid into the account as we decide how to utilize or island the microgrid or take advantage of the islanded, keeping the critical load up and running. This is the partners that we have. It's, we just kickstarting this project right now, and I'll give a quick overview of what we're looking at is, again, we're taking a resiliency metrics approach for the project. We're using a multiple network microgrids that's using a zonal approach that we island certain portions of the microgrid in order to keep the critical loads up and running. And by networking the multiple microgrids, also we increase the resiliency of the microgrid itself. And taking cybersecurity into account and how, as we start dealing with the smart reconfiguration and islanding, communication again becomes an important, and how do we look at what are the cybersecurity vulnerability associated with it, and how do we protect that? And of course, doing a field validation, first doing the hardware loop and control loop validation in the lab environment, and later on deploying it at the site. This is in Cordova, Alaska, where it's going to be deployed with then they will deploy it in the field and do the field validation. This is the approach. This is a concept approach. This is not exactly the microgrid that's going to be designed, but this is the approach we're looking at it, where we have multiple microgrids. In this case, it's two microgrids that are integrated together, networked together, and also tightly connected, also loosely connected through communication with other microgrids C and D. So looking over here, we're looking at 4 microgrids that are tied together, operate as one cohesive unit, but in the event of a fault condition, how do we increase its reliability and resiliency by connecting or taking advantage of multiple of those microgrids? Again, when I made about talking about multi-dimensional microgrid, initially when we first looked at it is looking at resiliency from how can we keep the critical loads up and running. Well, in this case, we're taking into account the multi-dimensional resiliency metric is a function of how to anticipate, withstand, and recover. So taking all those into account as we define the resiliency metric of the system and how do we recover from it. And here's a quick example of the approach we're taking. Again, the resiliency metrics is dynamically developed by using the anticipate, withstand, and recovery metrics, taking into account the historical data, the event information, real-time information. We collect all those together in order to compute the resiliency of the system and the metrics that's going to allow the behavior and the microgrid controller to behave. This is a little bit more, less crowded picture of it that take historical data, probabilistic data, real-time data, and compute all those as in real time in order to compute the resiliency metrics in order to decide how the microgrid controller should behave. This is just an example of what we're looking at. In this case, a very simplistic example. So in the case of you had a snowstorm, being Alaska, it's going to happen. So the PV panels are not working. So in the event that you have a PV panels not working, you will go ahead and connect to the neighboring microgrid that has more of a hydro generation, and once that's connected, in order to improve resiliency, how to also connect to the neighboring microgrid. So it looks like how do you do the switching, taking a simplistic approach over here, PV panel shadowing, and then how do you go ahead and recover from it. But it's get more complicated than that when you start looking at the event of critical loads, the time of day usage, and historical data as far as the utilization of the system. So it takes all those into account when you start doing the reconfiguration of the system. I want to close it with one slide that later on this afternoon at 1:30 we're going to talk about the grid modernization activity at the Department of Energy. And one of the work we're doing over there is the days of having one lab or one center or one entity have all the tools and assets in order to design system is becoming less and less realistic. So one approach we're taking is integrating multiple sites. In this case, we have three national labs, Idaho National Lab, Sandia, and NREL connected together, working with 5 universities, 3 in the US universities and 2 in Europe, where collectively we're solving one power system problem, utilizing asset of each other's tools. We're going to talk more about this in the afternoon, just quick overview of it. With that, I'm going to close and take your questions later on.